Hi everyone, welcome back to Geeks for Geeks. In this video, we will discuss the problem divisibility tree. So let us read this problem statement and understand what we have to do here. So problem says that we'll be given a tree with n nodes and the edges connecting them. Then the tree is rooted initially at the node 1. So basically the parent root node is the node 1, and our task is to remove the minimum number of edges from the given tree such that the tree converts into disjoint union tree so that the nodes of the connected components are divisible by 2. Okay, so if you will see this particular diagram that has been given, so initially the number of nodes has been given as 10 and we have been given the edges 2 comma 1, then 3 comma 1, then 4 comma 3, then 5 comma 2, then 6 comma 1, 7 comma 2, 8 comma 6, 9 comma 8 and 10 comma 8. So when you will draw the tree from these edges, so you can do what? You can make an adjacency list, and since you can see that the nodes have been given according to one based index, so we can subtract every node value by 1 in order to make the indexing 0 based, and then we can store all the nodes in an adjacency list. For example, in the adjacency list of 2 we can store 1, and in the adjacency list of 1 we can store 2, and this is how we can store our complete tree information in an adjacency list, because when we will try to iterate in the tree using the DFS approach, then that will be required. Now after this, if you will see, so the problem says that in this particular tree we have to tell that what is the minimum number of nodes that we need to remove such that the tree that has been given to us, it will get distributed into components such that every component has the total number of nodes which are divisible by 2. So if you will see here, let's say if I draw this diagram, so let's say if I have got let's say if I have got 1, okay, so let's say we have got 1, then what we have got is we have got the child as 3, then we have got 6, then after that we have got what? We have got 2, then we have got for 2 we have got the children as 7 and 5, okay, then for 6 we have got the child as 8, and then for 8 we have got the child as 9 and 10 here, okay, then for 3 we have got the child as 4. So let me just check this. So 1 3 4, then 1 6 8 9 10, then 2 7 8. So if this is the particular tree that has been given to you, so how can you solve it? So if you will see here, in this particular given tree, the basic thing is that whenever we have to remove the edges, so we will remove the edges whenever a particular component that is there, it is becoming what? It is having even number of edges, even number of nodes. Whenever a component has even number of edges, then we can remove even number of nodes, then we can remove its connectivity with the whole tree, correct? So then we can make it into a separate component. So if you will see here, whenever we will be iterating, so our children will always be telling us about the size. So when I'll be at the node 1, first of all I'll call for the child, so I'll call for 3. When I'll call for 3, then from 3 I'll call for 4. With respect to 4, there is no child, so the size will be returned as 0. Now 4 will return the size as what? It will return the size as 1. Then for 3, you can see that there is only one child, which is returning the size as 1, and 3 itself is a node, so now it will return the value as 2. So when it will return the value 2, that is the count of the nodes as 2, then you can say that yes, you can do what? You can do distribution here, and you can basically remove this particular edge here. So you can say that your count or your answer will become what? Your answer will become 1, because you are going to remove this particular edge between 1 to 3. So you can see that 3 and 4, this particular edge is going to become a separate connected component. Then after this, what will happen here is, when you will call for 6, 6 will call for 8, 8 will call for 9, 9 will call for 10. So 9 like basically 8 will call for 9 and 10 both. Now when you are at 9, so it will return the value as 1, which is not even. Then 10 will return the value as 1. Then 8 will return the value as 3, because total 3 nodes are there. Then after that, 6 will return what? 6 will return the value as 4. So when 6 returns an even number, then you can say that yes, you can distribute. So basically this will be your breaking point, because you can remove the edge between 1 to 6, and the moment you remove the edge between 1 to 6, then this particular connected component, you can say, has even number of nodes. So your answer will become 2, that you have removed 2 edges here so far. Then after that, what will happen is, when you will go to the third child of 1, that is 2. So with respect to 2, you can see here that it has the child as 7 and 5. So 7 will return the value as 1, and 5 will return the value as 1. Then 2 will return the value as 3. So since it returns the value as 3, so you can see that there is nothing even about it. There is no even number of nodes. So that's why you will not break. And you can see here that you have broken into 2 pieces. Basically, you have removed 2 connections that I will show in the highlighted color. So you can see that one edge that we had removed was between 1 to 3, and another edge that we had removed was between 1 to 6. And by doing this, all the connected components have now even number of nodes, because 3 and 4 there are two nodes, then 6, 8, 9, 10 have four nodes, then 1, 2, 7 and 5 have four nodes. So every connected component has got even number of nodes. I hope you have understood this idea clearly. Now let us try and quickly write this code. So first of all, you can see here that we have been given n nodes, and first of all we'll be making the adjacency list. So let's declare an adjacency list here. So we'll declare vector of int, let's say adjacency of size n, because there will be n nodes there. Then after this, what we'll do is we also need a visited array, because if we have visited a node already, then we don't want to visit it again. So that's why we can take a visited array, and initially we can mark it as 0, or you can say false. Then after this, what I can do here is, after this we can iterate through all the edges, let's say, and we can do what, auto I is to edges, right? So we can iterate through the edges, all the edges, and we can say that in the node, like in the adjacency list of u we will push v, and in the adjacency list of v we will push u, because this is an undirected graph. So what I can say here is that my u value will be what, it will be edge, it will be I of 0, that is the first part of the pair. Okay, then my v will be what, v will be basically I of 1. Okay, then after this, what I will do is I'll say that in the adjacency list of u minus 1, why I'm doing minus 1, because I want a zero base index. So in the adjacency list of u minus 1, I'll push back v minus 1, you can say. And then after this, we can do what, we can say that in the adjacency list of v minus 1, we'll push back what, we'll push back u minus 1. Why we are subtracting by 1, because we want the indexing to be zero based. Okay, then after this, we can simply call a dfs function from the starting point, and we can say that since in the one based indexed tree the root node was 1, so in the zero based index tree if I'm making, so the root node will be 0. So I'll start from 0, I'll pass the visited array, and I'll pass the adjacency list as well. Now after this, what will happen, my answer will get updated, and I'll return my answer, that is the total number of edges that I'll be removing. And initially I can mark my answer as what, 0 here. So before every traversal I can always mark my answer suppose as 0. Now once this part has been done, then we will talk about the dfs part, right? So in the dfs part, always it is going to return us the size, right? So we will say that we'll run a dfs call, and whenever we call for a whenever we are making a dfs call for a child, so it will always return the size of that particular subtree including that child, correct? So in that case, what we will do is we'll say that if we are currently at a particular node, right? So I'll always pass a current node, and then I'll pass the vector int ampersand visited array, which will help me to keep a track which nodes are already visited and which are not. And then I'll also pass an adjacency list, so vector int adjacency list. And then after this, what I'll do is I'll say that initially my count of the total number of nodes would be nothing but 0. Okay, and then after this, what we can say is that what will be the size of the subtree. So initially we can mark it as 0 suppose. Then what you can do is initially you can mark the current node as visited, so you can mark it as suppose 1. Okay, then we can iterate through all the nodes of the current node. So we can say that auto child is to adjacency of the current node. So I'll iterate through all the children in the adjacency list of the current node, and if the visited of the current is equal to 0, so if the if the visited of the current child is 0, so if the child is not visited, then in that case we can say that we need to run the dfs. So we can say that the count that we will get will be what, the count of the nodes that we'll get for the subtree of this particular child. For that we need to call the dfs for this particular child node. Okay, where we'll pass the visited array and we'll pass the adjacency list as well, and it will return us the count of the number of nodes that are there in the subtree of the child nodes. For example, when I will make a call here, let's say if I am making a call for the node 3 with respect to 1, 3 is the child, so when I'll make a call for it, so when the dfs for it will be over, it will return the value as 2, indicating that there are 2 nodes in the subtree. Then after that, if I call for the child one's child as 6, so when 6 is the child, so you can see that 6 will return the value as 4, because 6 has got total 4 number of nodes in its subtree. So every time when you get the subtree sizes, so you have to always add. So you can say that what you will do is you will say that size plus is equal to the counter. So you'll add this thing. Okay, let's say that if you want to do this, so let's say if what happens is if the count that you're getting, let's say if the number of nodes that you're getting in the subtree, if the count mod 2, suppose it's equal to 0, so in that case you can say that you will do result plus plus, because let's say if I'll take a result variable here, so if what happens is, if the count of the nodes in the subtree, in the child subtree, if it is even, then you can say that yes, you will be removing the node, so then you will do a result plus plus. Otherwise, if you are not going to remove, then you are going to do what? If you are not going to remove, then in that case you will say that you will increase your size, like you are going to say that in that case you will increase the size. So let's say if you have to increase the size, so let's say we'll have a size variable initially marking it as 0, and then what we can do is we can say that size plus is equal to the count here. So if we are not going to remove this particular connection, so we need to count the total size of the subtree. Okay, so basically whatever is the size of this subtree and other calls that I'll be making, I'll be adding them up in my size variable here, because this otherwise this particular subtree will be included in my current tree, because I'm not removing the connection. If I'm removing the connection, then I'll do result plus plus, indicating that I'm removing the connectivity, because I've got a even size component which has even number, total number of nodes as even. If not, then I'll include this thing in my size, so size plus is equal to result. And at the end of the day, before returning, what I need to do is I need to return size plus 1. Why? Because I'll remove the indicate the current node as well, right? So this is what I'm trying to do here. Let's try and compile this and check if it is working fine or not. Basically the idea was that if the number of nodes in a particular child component is what, if it is basically equal to if it is even in nature, then you will directly remove the connection. Otherwise you will keep on adding the all the components sizes one by one. So size plus is equal to counter, and before returning the final size you need to add 1 as well, because you'll include the current node as well. Okay, so I guess we are not getting the correct answer here because of some reason. So let me just check this part here. Maybe I might have made some mistakes here. So I understood the mistake that I had made last time. Let me just correct this part. Let's say when we had this thing, so I should always increase the answer here, right? And then it would work. And let's mark this as count. So let's remove this resultant variable. Okay, so basically the idea, I'm keeping the idea as same right now. What I've done is I already had the answer variable globally declared. So basically if the number of elements in that component is even, then I will remove this edge. So then I'll do answer plus plus. Otherwise I'll do what? I will do size plus is equal to, let's say, the counter that I've got. Okay, then let's try and compile it now and check if it is working fine or not. It should work fine now. Okay, so it says that a variable is not declared. Okay, so I'll declare the size variable initially as 0 now, and let's try and compile it to check if it is working fine or not. Okay, still there is a compilation error. Let's remove this and let's try and compile it again. So it's working fine now. Let's submit this. So basically I was making some variable mistakes. Now it would get accepted, I guess. Yes, so you can see that our code was able to pass all the test cases, and basically the time complexity would be order of n, because we are visiting every node exactly once, and the space complexity would be order of n as well for my code, because I'm using a DFS approach where I'm having the visited array space as well as I am using recursive stack space. So I hope you have understood this problem clearly. Make sure to comment down understood if you have understood clearly. If there are any doubts, please mention them in the comments and I'll clear them up for you. Thank you for watching this video.